Welcome back, everybody. Welcome back to the channel. So, before we get into today's episode, I just want to say that this week has been ridiculous. I've had tons of issues regarding the multi-threading platform, and since, as some of you guys know, I am working on a separate project that requires my multi-threading platform to work properly, and it hasn't. It's been a huge pain in the ass, so that's kind of why my videos have been choppy. I've been trying all week to fix them, and considering we're at this point in the tutorial series, I thought it'd be nice to actually have this stuff figured out. But I guess after a week of trying my hardest, I still haven't. I don't know what the hell's going on. So just keep that in mind that this threading system, although I've had it for years, it's pretty good, but it's not perfect. So I don't know exactly what we'll do. I don't want this video to be too long. We'll just kind of go through some of the various things in my multi-threading platform and just kind of see how far we get. So we're going to start off with, let's see, so I'm going to go to the CPP file and I'm going to scroll all the way to the top. So what am I? Oh, I'm at the top. Okay. So I have a bunch of imports here for this file. This file, the threading system, is going to basically be our entire language. It's going to consist of what's called our execution engine, and our execution engine is just going to be a infinite loop where we basically just execute a bunch of instructions. And we'll get into the execution engine probably a little bit later, so let's just look at a couple things. So first you want to create your thread ID field. As we kind of went over in the previous episode, you wanted to create a bunch of fields here, so you want to just initialize them to their default values. So our initial thread ID is going to be an illegal thread ID. Our max thread ID is going to be 0. Our thread self, now this is very important. So we're going to have what's called a thread local of thread self. I use this variable everywhere. Basically what that's going to represent is the current thread that is executing in the current scope, right? So obviously it uses a thread local keyword in C++, so this is going to point to the specific thread pointer that is referencing the current thread we're under. Of course, we want to create our hash map of our threads, and we want to create our thread stack size and our internal stack size. And we also want to set up our thread monitor as a recursive mutex. Now, one of the things that I've been experiencing with regards to my threading system being very crappy this week is the internal stack size turned out to be a bit too much. When I'm using my multi-threading or my task scheduling API, it creates a bunch of tasks, and those are representing a bunch of smart threads where you can run multiple tasks on a single thread and do a bunch of other stuff. But what's important is that this was once 1 megabyte, and that turned out to be too much. Literally, if you have a processor like on mine, an i7 with multiple cores, once you create all of the threads necessary, you're going to be allocating a megabyte per thread, and that's really going to bog down the memory system. So just keep that in mind. I put mine at 200 kilobytes. So if we go back, so now we want to also create a array of registers. So we're going to have a total of 12 registers. It's literally just an array of doubles. That's it. We also want to create a startup function. So this is actually used in our virtual machine. So we can just go over that now. So in our virtual machine, when we start up everything in the beginning, we of course process our executable. We do a check for our internal stack size. We've already gone over that. And then we start up the multi-threading system. So what this does is what the hell? Okay. We want to initialize our multi-threading system by putting in the thread map size, and yeah, so you want to initialize that. That just calls the init function, which just obviously initializes the hash map. Then we want to create a thread pointer of our main thread. We want to malloc one thread, and we want to assign that as our main thread here. And then we want to do what's called a create. So when it comes to creating threads, we're going to have a couple different ways to create threads. Let's just go over the basic one. This is at the high level. So there's basically going to be two main ways to create threads. There's the high level version and the low level version. The low level version is going to basically mean creating a thread by passing in, what is this, the method address, the main method address, and the daemon, whether or not it's a daemon thread. And the high level, basically, we pass in a string representing the name of the thread, and then a method pointer representing the actual method or main method that we're going to start with. So That's kind of how it works. So what I basically do is I get a thread ID. So here's how I basically generate a unique ID for every thread. So I create this generate ID function, which sets a guard on the thread monitor. So this is the first example where we see the thread monitor. The thread monitor is a global static field that we use to kind of do basic things in the multi-threading platform just to make sure everything is synchronized properly. So if we go into guard, all it does is it creates a std lock guard of a recursive mutex and a guard field, and we just pass in the mutex or whatever the name of it that we passed in here. And yeah, so that's kind of how that works. So we create a guard of this, which once we do that, we want to create a thread and whether or not we've wrapped. And what I do is the basic way of how I create my threading system or how my threading system works is we're going to have a bunch of threads. So here, I'm going to create this one, and I'm going to create a couple of boxes that are going to represent several different threads in our program. So at the very beginning, we're going to have the main thread, which is going to have an address of 0. After that, we're most likely going to have our GC or our garbage collector, which is going to be a thread of 1. And then finally, we're going to have the JIT, which is our just-in-time compiler, which is going to have a value of 2. Now, as we're generating these addresses, we're going to need to obviously continuously increment the address value of each thread. But there's a problem. What happens when you, let's say, this is like, whatever. And for the sake of argument, I think I did more than that. But yeah, you guys get the point. So for the sake of the argument, let's say the maximum amount of, the max int value of a thread ID, even though I know it's an int32, int32 is 2 billion, I believe, but whatever the maximum value of the n is, let's assume it's 1 million. What happens when we cross that 1 million value? Well, the ID is going to circle back around to 0, right? So we want to basically protect against that. That's why I have this wrapped Boolean here. And we basically want to reuse a previous ID. The basic conundrum that we end up facing as we're creating threads is, let's say for the sake of example, this is thread ID of 3. Well, once this thread exits, that ID is what I consider a burned ID, meaning that we've used this ID, and even though that ID is in fact available, we won't be able to reuse that thread ID until we go and wrap back around to 0 and go all the way back up the list from 0 to reuse that burned ID. So that's kind of how it works. So basically, once we try to generate it, if we wrap back around, like I said, we'll just go from 0 onwards. So what we do is I say while get thread ID plus plus. So I pre-increment the value and I call get, and that assigns this local field here, and it takes a reference to that, so that way it actually assigns the value. And I basically check to see if the thread ID is less than 0. Then if so, then while I'm doing this, I basically check to see if the thread ID is less than 0. If so, then it's obviously wrapped. And if we've wrapped once, that means that we've gone through this entire list of threads, and all of these threads have values, which again is extraordinarily unlikely, but you do have to cover this. And if we wrap around and we do it again, and we still haven't figured out what the ID of the thread is, then we're going to just return an illegal thread ID. In the case where we're just wrapping for the first time, we'll say wrapped is equal to true, and then the ID is equal to JIT thread ID, meaning that once we get back up here, we're going to pre-append the value, and we're going to start from the next thread after the JIT's address, because obviously none of these threads from 0 to 2 will never be available. So hopefully I've explained what that is and how it works. So that's how I basically generate thread IDs. So if I go back, so now we want to check to see if the thread ID is equal to illegal thread ID. Then of course we return. So with initialization, this is a basic quick function where I can initialize a thread. So I can say the name of the thread, what's the ID of the thread, what's the main method, whether or not it's a daemon thread, and whether or not to initialize the stack. That's going to be the stack pointer and the frame pointer and then the actual stack. That's to initialize everything. And of course, we just initialize the fields. So I call the basic init function, which sets up the entire object. And then once I do that, then based on that, I do whatever I need to do in here. So I set up the name, the ID, the main method, the stack limit, and whether or not it's a daemon thread. By the way, if any of you guys don't know, daemon threads in my programming language basically represent special privilege threads, meaning that they can't be killed, they can't be shut down or anything. So there's some rules for daemon threads that I created. They're completely arbitrary, by the way. I know Java does this, Android also does this, so I don't know, I just copied it, I guess. This is leftover code from the Dalvik VM, so I just left it in. But yeah, so we have that, and then we also want to initialize the stack. So if we have the build JIT flag set to true, then we want to set our JIT context equal to a new JIT context. Now, my JIT is not built right now. We'll get into what a JIT context is at a later date. You can just probably put this if def block in here and it won't break your code because it won't be defined. And you can ignore this sharp profiler. We won't really talk about that. And of course, you can see here, I basically do a basic setup for the data stack. I just call calloc on there, and I pass in the total internal stack size and the size of the stack element as the bytes. Now, this is not your normal calloc function. This is actually a calloc and malloc and realloc function that I created in my virtual machine. So basically what these three functions are, they are all exactly the same. The only difference is how the function is called. Basically, we can go through all three of these now. The premise of doing this is that as we're allocating data in our virtual machine, we want to be able to keep track of all of the things that we're allocating. So what we do is we basically say garbage collector. So what we do is we set up some variables here, and then we basically check to see if the garbage collector dot self is not equal to null. What that represents is that is the singleton value of the garbage collector. If that's not equal to null, then we try to see if space is available for the bytes that we're trying to allocate. And what that does is that basically just checks to see if the bytes plus the managed bytes of the bytes that we're managing here is less than the memory limit, which is just the maximum amount of memory that we have for the garbage collector. So if I go back, so that's what we do. And then if we don't have any space available, because of course I have a not here, then we go to low memory. And now before we get there, we basically want to just assign the pointer field to the malloc value that we passed in here. And the reason why I created a variable is because down here, I check to see if the garbage collector self is not equal to null. If it is and the pointer is equal to null, then what I do is I do some checks to see if we can actually try to do some stuff and then try to allocate the data once more. So what it's going to do is it's going to basically check to see if we have the garbage collector, or I check to see if the GC is set to false. And that's going to represent, did we try to do a garbage collection? Then if GC is set to true, then we basically say out of memory. Now, here's how it works, right? So we come up here, we don't have any space available, we go to low memory, or we do have space available and pointer is equal to null. We come down here, GC is going to be false by default, and we're going to set GC to true, and then we're going to try to force a garbage collection on demand to try to basically see if we can free up some space to allocate the thing that we're trying to allocate. So I basically check to see if the VM state is equal to running, and if the VM is actually running, then I also check to see if the garbage collector is also not equal to null. If so, then I basically do a self collect, and I basically pass it a GC low. Now, we'll get into the garbage collector later and how it works, but I basically have three tiers of garbage collection. I have what's called a low garbage collection, which suspends and resumes all threads. So it basically shuts down the entire application temporarily and collects some garbage and then basically starts it back up again. This is the same thing that the Java virtual machine does. This is why if you have a game and you have poor memory allocation with your game, you'll have hitches in the frames because it's constantly shutting down all of the threads for a short amount of time. So of course you'll drop frames that way. I also have an explicit garbage collection, which is called by the actual garbage collector itself, and a concurrent garbage collection, which basically meaning that we're going to just fire off a garbage collection and let the actual garbage collector do the work instead of forcing a on demand on the thread that's actually calling it. So basically meaning that we'll do a concurrent garbage collection and a background thread. It's going to be done by the garbage collector itself. We'll get into it later. I don't want to get too much into that. Once we do the collection, then we go back up to the top to alloc bytes. We then try to see yet again, is the garbage collector instance not equal to null? Do we have any space available? And this could have changed, right? If we do a collection, we're going to have more space. So there's potential that this could be set to true, and we skip over this if statement. If it isn't though, then we go to low memory, and when we do, we'll just immediately say out of memory. So that's kind of how it works. It's the exact same way for all of these. The only difference is that I basically just call the respective function. That's it. So all of these are the same. It's very important to add these though, because that allows us to basically keep track of, making sure we don't over allocate memory. And this goes for any piece of data that I'd like to allocate. Now, this doesn't involve memory tracking, right? Because just because I allocate it, as you see, I don't record that memory allocation. So we'll have to see how I do memory tracking a little at a later date. But yeah, so that's in it. And let's see. So if I go back up to the top, where is the actual thing? Okay. So go back up here, go back to create. So once we've initialized our thread, then we want to push the thread, which basically passes in the current instance of the thread. We guard the thread monitor, and then we just add the thread to the hash map. So that's what I do for that. And of course, I do it by ID because each thread ID is going to be 100% unique. The thread ID is what we're going to be using at the high level as a way to reference the hard physical address to the thread to be able to manipulate it. So we have that. So let's go back up to the top. So once we basically have created our first thread, we want to set the priority to our thread priority high. That's going to be this value. And we want to set the main thread to high by default because that's just a personal decision. You guys can do whatever you want, but that's what I have. So once we do that, then that's basically it. So now before we get to the other two creates, I want to mention something. So this create here at the high level does not do anything. It doesn't go the extra mile and actually do stuff that the other threads would actually do. Meaning that if I go to this create function, and this is static versus these which aren't static, but if I go to this one where I pass in basically the method address and the daemon, as you can see here, it does a lot more stuff. It does a lot more checks to make sure that things are actually the way they're supposed to be. So here's how I basically connect the high level to the low level in my programming language. So of course, I would call this function using a system interrupt through my virtual machine, and I would get the thread ID by generating it, and I would set CMT equal to false. The CMT register is going to be what I use the compute register to basically return the result value of how successful was the transaction for creating the thread. If I get all the way to the bottom, I'll say, yes, I was successfully able to create the thread. Otherwise, I'll return a bad value here and it'll just be false and we can inspect whatever the value was. So I basically want to check to see if the method address is less than 0 or if the method address is greater than or equal to the manifest.methods, which means the total methods in our current program. And if so, then I say result thread create failed, obviously because you can't create a thread with an invalid main method. You also want to make sure the thread ID is not invalid. So we do that. I return this result. And again, guys, these values are arbitrary. They don't mean anything. I just made them up. So you guys can put whatever you want. But these are the values that I have. So there's that. Let's see. So we also want to basically set up our thread. So we want to set the main method based on getting the address of whatever it is in the main methods field here from the virtual machine. And then we want to check to see if the param size is not equal to 0. It's very important. So when it comes to the main method for my programming language, it cannot have any parameters, basically. If you want to pass any information to that thread at the start, you're going to have to use my multi-threading system in order to appropriately transmit data from one thread to another upon start. And we'll talk about it a little bit later on how this kind of works to basically transmit data from one thread to another by creating it and starting it. It's a whole process, but yeah, so we're starting to get to a point to where we're going to have to start creating what's called contracts, or basically code that works in a specific way to conform to a specific pattern. So for instance, as you see, I have a bunch of different constructors. If I want to pass it a set of arguments, I would have to basically say, here's the name of the thread, here's the actual function that we're going to be calling, and then when I go to start it, I'm going to pass in the arguments here. But there's a lot of things that are happening behind the scenes that basically make all of this stuff work together. So I'm just saying that to say that in order for this system to work, you're going to have to plan out your entire system from top to bottom. For me, I make sure that I don't have any parameters for my main methods. And in my opinion, this is the easiest way to do it. You don't want to have parameters for your main method because it makes it harder to pass data to that actual thread, because how are you going to pass information? I mean, you could do it at the low level, but yeah, whatever. That's what I do. So you want to create your thread, and then you set the name equal to thread at whatever the ID is, and then we initialize the value by setting the name, the ID, the main method, and the daemon. That calls this function that we just went over. Then you want to push the thread, which basically adds it to the threads list. You want to set CMT to true because obviously we were successful. Otherwise, if you want to create a daemon, which I think this is the last one, we basically want to generate an ID, check to see if the ID is not illegal. If so, return. Otherwise, we just initialize and push, and that's it. So those are various different ways of how we create threads. So hope you guys enjoyed the video. As usual, if you have any questions, as always, put them in the comment section below. And of course, if you guys would love to help support the channel, you can always head over to my GitHub repository at androidevcd/sharp. And when you do, definitely watch, star, and fork this repository. That gives this language a lot more visibility and let other developers know this language exists. Also, if you guys are curious about some of the stuff that I'm looking to add in the future, you can always head over to the roadmap section, and this kind of contains all of the new things that I'm looking to add and improve in the actual language for the future. So definitely recommend checking this out. It gives you a lot of insight into what I'm actually looking to add later on. So that's going to be it for today. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.